This lesson covers Unit 1.2 Scientific Notation and Conversions. So first we're going to start with scientific notation. So scientific notation is just used to write very large or very small numbers in a more concise way instead of including all of the placeholder zeros. We can just write it in a shorter, like kind of a shorthand way. So this first part of the number that we see that comes before the multiplication sign, this is known as the coefficient. And in order for it to be in proper scientific notation, the coefficient does need to be a number between 1 and 10, but this also reports the sig figs. So we've already had a little bit of practice with identifying the number of sig figs with a scientific notation number, so that coefficient lets us know how many sig figs are being utilized in this measurement. So for this example, because we have 7.4, we would report 2 sig figs. Okay, the other part of our problem is always going to be a base 10. And looking at the exponent, we can kind of make snap judgments about if it is a large or small number based on that exponent. So if we have a positive exponent, it's going to make the number larger, or it's going to be a larger number. And when we go to put scientific notation into standard notation, we'll see that we're going to move the decimal to the right, okay, in order to make that coefficient number a larger number. Okay, if we have a negative exponent, generally when we see negative exponents, you should think of very small numbers. Usually it's going to be smaller than 1, so it's going to be a decimal number. And if we were to convert this scientific notation with a negative exponent, we're going to move the decimal to the left. So when we are looking at scientific notation, sometimes the numbers are not using proper scientific notation. So here, for these 3 separate examples, we're going to look at what is wrong and why it doesn't have proper scientific notation. So for the first part, we have the coefficient 40.8 does not fall between 1 and 10, so that would be the problem with the scientific notation. We would need to move the decimal over 1 and increase our exponent that is found on the base 10. Okay, for the next one, we have 1 times 5 to the second, so the base is not 10. So this is not scientific notation. And then lastly, again, our coefficient is not between 1 and 10, so it is also in the wrong notation. So when we are converting between scientific notation and standard notation, I kind of already talked about this, but the positive exponent, it's going to make the number larger, so we're going to move the decimal to the right. Whereas with negative exponent, it is going to make the number smaller, so we're going to move the decimal to the left, generally making it a decimal, so a smaller than 1 number. So when you are moving decimals, I know this is very apparent, but if there is no decimal in your coefficient, so for example, this 5 here, it's understood that the decimal is after the 5. I know that's kind of a no-duh statement, but a lot of times I see that students will actually start their decimal out here. Even though if I'd ask them where the decimal is, they would tell me it's after the 5, but just sometimes whenever they get in the flow of things, they kind of just forget. If there is no decimal given, they sometimes start on the wrong side of the coefficient. So just remember, if there's no given decimal, it is at the end. So for this one, we're going to move our decimal 3 places to the right. So if my decimal is here, I'm going to move it 1, 2, 3. So here's my new decimal, which means that for each of these loops, these are, we need placeholder zeros, okay, in order to change the number into 5,000. For this next one, I have 2.137. Again, I'm going to make this number larger by moving the decimal to the right 2 places in this case. So 1, 2. I'm going to have 213.7. Okay, for the negative exponent, I'm going to be moving the decimal to the left. So I have 5. Okay, this is usually where people put the decimal in the wrong spot. So my decimal is here, and I'm going to move it 3 places to the left in order to make it a smaller number. So 1, 2, 3. In my empty loops, I'm going to fill in my placeholder zeros. Okay, and then with this number, 2.13, again, I am going to be moving my decimal place to the left. In this case, 2 places, so 1, 2. So I only need 1 placeholder 0 in order to complete the standard notation. Okay, when I'm going in the opposite, so going from standard notation to scientific notation, the first step is we need to place the new decimal to create a coefficient between 1 and 10. We then count the number of places the decimal moved from its original spot. If it moved to the right, the exponent is negative. If it moved to the left, the exponent is positive. And a lot of times, too, we can just look at the number. If it is a big number, meaning it's greater than 1, we're going to have a positive exponent. If it is a small number, meaning it's a decimal, it's less than 1, we're going to have a negative exponent on that base 10. We do want to keep the original sig figs, so we'll be kind of discussing how we do that as well. So for the first one, I have, let's see, what is that, 4,010,000. And so I know in order to get my coefficient between 1 and 10, I'm going to want to place the decimal between the 4 and the 0. My original sig figs, I have 3. Because the 4 counts, the 1 counts, the 0 is sandwiched. All of these fall off because there's no decimal holding them on. So I have 3 sig figs. So I'm going to report 3 sig figs with my coefficient. So 4.01 and then times 10, and then I got to figure out how many times I moved the decimal. This is a very large number, so I know it's going to be a positive exponent. So my old decimal was at the end. I moved it 1, 2, 3, 4, 5, 6 times. So I'll have times 10 to the 6th power. Okay, for this next one, looking at sig figs, I do have a decimal, which means it's going to hold on to these trailing zeros. So all of these zeros are significant. So we have 4 sig figs. So we're going to report 4 sig figs. My new decimal needs to go between the 3 and the 0 in order to create a coefficient between 1 and 10. So 3.000, because I do need to include all of those to have 4 sig figs, times 10, and then I'm going to count how many times I moved it. This is a number bigger than 1, so I know my exponent is going to be positive, and I moved it 2 times. Okay, for the next one, looking at sig figs, remember that leading zeros do not count. Trailing zeros do count if there's a decimal somewhere in the number, which there are. So I'm going to have 3 sig figs that I'm reporting. In order to create my new coefficient, I'm going to stick my decimal between the 1 and the 0. So 1.00, including my 3 sig figs, times 10. My original number is less than 1. It is a decimal number, so I know it's going to be a negative exponent. And I'm going to count how many times I move my decimal. 1, 2, so -2. The next one is also a decimal, so I know I'm going to have a negative exponent. Looking at sig figs, my leading zeros do not count, which means I just have 3 sig figs, the 2, 3, 8. My new decimal is going to go between the 2 and the 3, so 2.38 times 10. I know it's going to be a negative exponent because my starting number is small, and I moved 1, 2, 3 places to the right. Okay, for these next ones, we're going to be multiplying, so putting it into your calculator. Make sure you understand how to put it in correctly into your calculator. If you're using a scientific calculator, how I would put it in, and I like to use parentheses, but I would do parentheses and then 4, and then to do the times 10, you can do second, EE. It's the button just above the 7. So second, and then EE, and then type in 3, parentheses, and then times, parentheses, 8, second, EE, 5, and then the E just stands for times 10. So it's just a faster notation for putting it into your calculator. It also ensures that there's less error, human error, whenever you're typing in the problem. But if we go ahead and type this in, I get 3.2 times 10 to the 9th. Okay, so it actually reports my answer in scientific notation, which is nice whenever you're using a scientific calculator. But looking back at my original problem, looking at sig figs, I have 1 sig fig here, 1 sig fig here. So my answer needs to have the least number of sig figs in the given problem, which would be 1. So the 3.2 is going to round down to 3. So my answer in correct sig figs will be 3 times 10 to the 9th power. For division, same thing. Again, make sure you're using parentheses. Again, I would use the second EE in order to do the times 10. But when I put this in, I am going to report 2 sig figs in this case. This number has 3 sig figs. This one has 2. So 2 is my least number of sig figs. So that's what I would include. I'm going to have 4.7 times 10 to the first. Okay, so I wrote it in scientific notation. Okay, for this next part, this is unit conversions. And this up here, you have this on your half sheet. It's going to be your lengths, your mass, and your volume. So some of them are going in like metric system. Some of them are going in the empirical system. So here in the US, for the most part, we use an empirical system for stuff, but you're going to have to sometimes convert. We usually use metric system in physics. So a lot of times you might have to convert units. So these are all the conversions for that. And you'll see the ones that go, like, for example, like here, this one, miles to kilometers, or miles, inches to centimeters. Those both are converting from imperial to metric. Same thing with like kilograms to pounds. That's also doing that. And then we also have one for volume. I believe it's, gallons to liters. So with the conversion chart in the metric system, what's nice about the metric system is that it's based on base 10. So we're really just moving decimal places to go among the different things compared to the imperial system where you have to know that there are 12 inches in 1 foot. So looking at this base scale, we're going to just go through the ones that you will probably encounter in physics. So we have mega, okay, which is represented with a capital M. And then that one you can see, you can kind of count from the base how many times we would move our decimal to get to mega. And then we have kilo or kilo. This one you're probably aware of or you've used in other classes, such as a chemistry class if you've had chemistry. And then we also have deca, deci, centi, milli, and then micro. Okay, so these will all have another letter that comes after them. So for example, for like kilo, we can have kilogram, kilometer, kiloliter. For milli, we can have millimeter, milliliter. And then our base is our base units for length, mass, and volume. So our base for length is going to be meter. For mass, it's going to be gram. And for volume, it's going to be liter. Okay, so let's practice converting. These, you'll notice, they're all in the metric system. So we're just moving decimal places. And then reporting our answer with the correct number of sig figs. So for this first one, we only have 1 sig fig. We're going to start at centimeters and we're going to kilometers. So what you want to do is you want to put your finger where we're starting, at centimeter, and then you want to count your way up to where we're trying to go. And notice we're moving the decimal to the left, and we're actually going to move the decimal to the left in our problem. Okay, so I'm starting at centimeters, and I'm going to move my decimal 1, 2, 3, 4, 5. So if I move this decimal, I'm going to move it 1, 2, 3, 4, and 5. I do have an open loop, so I will need to include a placeholder 0, so 0.04. Okay, and my answer does have 1 sig fig, just like the original. Okay, for the next one, I have 350 grams to kilograms, grams. Anytime that you see just a single letter like gram, liter, meter, we're starting at base. The one that throws people off is the meter. They'll see the M and they'll start here. But this is millimeter, not meter. So make sure if you see one letter like L, G, or M that you're starting at base. So we're going from grams, which is base, to kilograms, which is here. So I'm going to move my decimal 1, 2, 3 to the left. So 1, 2, 3 to the left. I had 2 sig figs to start, so 0.35 would be my answer. For the next one, I'm going from kilometers, which is here, to meters. It's just a single letter, so it's base. I'm going to move my decimal 1, 2, 3, but to the right this time. So from here, 1, 2, 3. I'm actually going to have 2 open loops. So I'm going to have 1200. Make sure you don't put a decimal because we only want to report 2 sig figs. So those 2 zeros are just placeholders. Okay, and then lastly, we have liters to milliliters. Liters is at base, milliliters is here. So we're going to move 1, 2, 3 to the right. So 1, 2, 3. I have 1 open loop. So 450. And again, 2 sig figs, so we don't need a decimal after that. Okay, converting. When we're converting, we're going to be using ladder systems in order to convert. So for this practice problem, how many hours are in 0.025 years? So we're going to start with the number that they've given us. So 0.025 years. And put it over 1. Whatever we start with, so years, it's going to drop down in order to be canceled, okay? And so we have to use a conversion factor that we know for time. So I know how many, I don't necessarily know how many hours are in a year. If you did, you could use that conversion right away. But I do know how many days are in a year. So in 1 year, there are 365 days. Okay, so the years cancel, so now I'm in days, but I want to get to hours. So in 1 day, because the day has to drop down to the denominator, there are 24 hours in 1 day. So the days cancel, now I'm left in hours. So if I multiply across the top, multiply across the bottom's just going to be 1, so I don't need to worry about dividing anything. I get 219, but if I look back at my answer, or at my original problem, I had 2 sig figs because the leading zeros don't count. So my 219 is going to round up to 220 hours. First, next one, a certain map has the following scales. They're basically giving us our own kind of like made up conversion factor. For every inch, that is equal to 5.5 miles on this map. So if the distance between city ABC and XYZ is 12.6 on the map, what's the distance in miles between the two cities? So we're going to start with what we were given. So the distance on the map is 12.6 inches over 1. Okay, so for the conversion, because I'm in inches, I have to drop that down to the denominator, and I'm trying to go to miles. So I'm going to plug in the conversion factor, the scale that they gave me here. Okay, so 1 inch is equal to 5.5 miles. Okay, you probably could have just thought this through in your head and realized like, oh, I just need to multiply those two numbers and I can determine the miles, and that's fine. But I do always just suggest setting up the ladder to just ensure that you're doing the correct thing, that you're multiplying when you're supposed to multiply and dividing when you're supposed to divide. So in this case, I'm just going to be multiplying, and I got 69.3 miles. But looking at our conversion factor, I only have two sig figs, or the conversion factor does not count for our sig figs. These are unlimited sig figs because we just take them as like what they are for conversion factors. So only the numbers that are given in the problem are going to be the ones that help determine. So this has 3 sig figs, so this answer will also have 3 sig figs. All right, for additional practice, converting, we're going to be using the chart up above, the unit conversion chart, to set up our ladders for this. So we're going to start with 180 inches over 1. Okay, and looking up at our conversion chart, I'm trying to go to yards. So I do have inches to feet, and then I have feet to yards. So that's, let me actually scroll up here. So here in the length portion, I know that there are 12 inches in 1 foot, and there are 3 feet in 1 yard. So I'm going to set up 2 conversion step ladders. So 12 inches in 1 foot. So the inches cancel, and then feet drops down, and I'm going to yards, and 1 yard is equal to 3 feet. So in this case, I'm going to take 180 divided by 12 times 3, and I got 5.0. I do need to include the 0.0 because I need to report 2 sig figs because my initial measurement had 2 sig figs. Okay, for the next one, I have 9,000 feet is equal to how many kilometers? I am going from imperial feet to metric kilometers. So looking up at my lengths, I know I'm going to be using one of these for my conversion factor. So I actually converted to feet. Or the feet to miles and then miles to kilometers. There are other paths that you could take, and you should get a very similar answer. It might be slightly different, but I'm going to go ahead and do that. So I'm going to start with 9,000 feet, put it over 1. And my conversion factor, there are 5,280 feet in 1 mile. So then from there, I can go from miles to kilometer, and the conversion factor states that 1 mile, because the mile has to drop down, is equal to 1.609 kilometers. Okay, so my feet cancel, my miles cancel, I'm left in kilometers, which is what I want. So I'm going to multiply 9,000 times the 1.609 and then divide that by 5,280. I am going to report 4 sig figs because this decimal here lets us know that all of these are significant because the trailing zeros would hold on. So we're going to report 4 sig figs, and I got 2.743. Okay, this last one is a little bit trickier because we're actually going to be converting 2 things. So we have 30 feet per second, and we're going to change it to miles per hour. Okay, one thing you need to understand is that miles per hour is just this. Okay, sometimes the MPH kind of throws people off, but it is just a distance unit divided by a time unit. So I'm going to go ahead and write in my first one, and we're going to write it a little bit different than we did before because we actually have something we're going to put in the denominator other than just the 1. So we're going to have 30 feet per 1 second. Okay, so the seconds actually go in that denominator. So we'll go ahead and take care of the seconds first. We want to convert them to hours. Now, because the seconds are in the denominator, this means that they need to move up to the numerator in order for them to cancel. So I'm going to go from seconds to hours. So seconds to hours. And I know, and this is a number that you're going to need to memorize, or else you're going to just have to do more steps to the ladder. But there are 3,600 seconds in 1 hour. So that number here is an important number. You should memorize this conversion factor. It's not going to be on your paper, your conversion paper. It's just something that I expect you to learn. And then, so my seconds are now in hours, but now I need to convert my feet into miles. So I do have a conversion from miles, or from feet to miles. And so feet needs to go on the denominator because it's up in the numerator, so I need them to cancel. So there are 5,280 feet in 1 mile. Okay, so now I'm going to just multiply across because my feet have canceled. I now have miles. Oops. Reverse. I have miles over hours, which is what I want. So I'm going to take the 30 times the 3,600 and then divide by the 5,280. My original answer was 1 sig fig, so I'm going to round my answer to 1 sig fig to get 20.